There we go. I will begin with a word of prayer. So I get up here. Dear Heavenly Father, we thank you for this day. Again, I thank you for these students. Just ask you to be blessed today by this class, that we glorify you in what we do. And again, I just thank you for math, for your creation, and for all your many blessings, Lord. In your name I pray, Lord Jesus. Amen. So, any questions? Let me just get some sort of bookkeeping stuff out of the way. So I noticed that my email in my labs was from my old institution. So if you sent me something through my labs, like some kind of like ask your instructor message or something, I didn't get those. However, I should start getting them now because I changed the email to Liberty email, so I should see it. Of course, as a general point of order, if you send me a message through some sort of, whether it's whether you use Canvas, however that's done, or one of the electronic homework systems or whatever else, if I don't respond to you, right, that probably means I didn't get your message for whatever reason, right? So the next thing you should do is just email me directly. Yeah. And like, when I say don't respond to you, I mean like within like a day. I almost always respond to messages within a day. So, if I don't, email me. Every so often, you'll email a professor here, and then the email system will eat your message. So like it's not uncommon in the past for me to open up email around Christmas and then like notice that there's an email that I never saw that didn't pop up in my inbox from like 3 months ago. Every so often they just kind of like don't filter to the top for whatever reason, and you just don't see it. I mean, it is possible for messages to go out there and just ping pong around for like a long time. It's not usual, but it can happen. If you ever have a professor not respond to you after like a day or two, email them again and find out if they actually got your message or not. Like sometimes they don't. There's other more simple things too, like my wife's email is really close to another instructor. So people will email the other instructor thinking that they email my wife, and of course the other instructor will not respond to them necessarily. Because it's not actually an instructor, it's actually like a student who's no longer at Liberty, but they still have an email associated with them. So these sorts of things also happen. Anyway, there's that. The other thing is a lot of you have had concerns about like grades not appearing in Canvas versus my labs. So in summary, I would say this: the grades in my labs are real. They will eventually transfer over to Canvas if they haven't already. As a general point of order, I think they'll transfer whenever the due date is, but if I give an extension, then that bumps the due date back, right? Other exceptions to this rule: if I hit the sync button before the due date, it will like, whatever work you've already done, it puts it over to Canvas, right? So you might have a 13 in Canvas, and you might have a 40 in my labs. The 40 is real. The 13 is just an artifact of it copying your score from a previous time. So relax, it will come over to Canvas in time. It's going there. So anyway, just wanted to try to clarify that. Any questions? Have a good weekend? Yeah, okay. I'm happy. I sold a house, so that's done. All right, so here we go. Inequalities. And interval notation. If you haven't top hatted already, please do so. As you can see, the exciting top hat code is over there, 2023. All right, so what I'm going to do is I'm going to draw a bunch of number lines here, and I'm going to illustrate different kinds of intervals with a picture. Oh, I'll probably do 6 of them. That should suffice, I think. If I do 6, that'll probably do it for us. So these are just number lines, all right? And so the first one I'll start with is you might have something that looks like this. All right, it goes from A to B, like so. Here's a typical point X. All right, I can write the following mathematical sentence. X is an element of the closed interval from A to B. which by the way is defined to be x such that a is less than or equal to x is less than or equal to b. All right. Just in case you don't know, let me mention this funny looking symbol right here means element of. And this right here you can read as such that. So this is the so-called set builder notation. You know, you put the elements that are in the set to the left of the such that bar, and then to the right you put whatever condition you want to describe the elements with. In this case, a less than or equal to x less than or equal to b. And this is the closed interval from a to b. Now what else could we do? We could do like this, right? We could exclude a and b. In the previous one, a and b were included, all right? Now here, a and b are excluded. They're not included. Here we have strict inequalities, right? So a is not equal to x and a is not equal to b in this set, right? This is also known as the open interval from a to b. What else could you do? How about this? We could do a to b like that. Then what would the situation be? So this time we would allow equality on the a, but not on the b. So b would be excluded, whereas a would be included. All right? Now there's one other like this, but I'm going to skip it. So I'm going to go straight to the infinite ones. We could have something like this, right? Start at a and go all the way over here to infinity. All right? So I've been meaning to draw x as a typical x in each one of these. Here this means x is an element of a not included to infinity, right? And that's just x such that x is greater than a. All right, now I'll let you guys choose. What should I do next? We could go to minus infinity, right? Starting at, do you want to include a or exclude a? Your choice. Include, okay. I like that. Good choice. So that would look something like this. Here's your typical point x. X is an element minus infinity to a included. And that would be x such that x is less than or equal to a. And lest I forget, there's also the possibility that we have what? Everything, right? Everything. So that would just be this, right? So there's no condition on x at all except that x is a real number. And our notation for that, remember, is just minus infinity to infinity. There's another symbol for that, which is just this funny looking r. That's the set of real numbers. Can you guys think of any other? I mean, there's like 9 of these actually. So what have I not done? I've not done, let me just write down the patterns without writing everything else, okay? Like the patterns I missed were what? We could also do like this, right? Or what else could we do? We could have done like this guy, right? Or we could have done like that guy. That kind of pattern, right? Sorry, am I where you guys can't see? You go, okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's actually one other, it's very silly. But I think, I mean, it depends on whether or not, what book you read, but some people would consider just the set just containing a to be an interval. Right? Some wouldn't, but that's something, that's a possibility that will show up in our solutions. Like sometimes we just have one isolated point as part of our solution to the things we'll look at, okay? It can happen. There is one other thing that I would say is not an interval, but is also a necessary like set to talk about, which is the empty set. Sometimes there's no solution, right? So if there's no solution at all, we use the empty set for the solution set. But if you're asked to give your answer in interval notation, what we're asking for is the part I'll underline in green, right? This is the interval notation, interval notation, interval notation, interval notation, interval notation, interval notation, right? Anyway, I'll be showing you interval notation in all the examples today, pretty much, right? So another way to say this is the intervals, there's the sets of real numbers that you can draw on the number line with one continuous stroke of your pen without lifting the pen or pencil, right? There's no jumps in these intervals. Intervals are connected subsets of real numbers. So here's laws of inequality. So I'll start with a very silly one, but a necessary one. A less than or equal to B is interchangeable with B greater than or equal to A, right? One of the things we can do is we can trade less than or equal to for greater than or equal to, provided we what? We flip the left-hand side with the right-hand side, right? So this is something you should keep in mind. We do use this a fair amount. Another thing we can do is if we have A is less than or equal to B, then we can say A plus or minus C is less than or equal to B plus or minus C. So we can add or subtract the same value across an inequality, all right? And this is another thing we can do. Okay, just like with equations, right? We could add or subtract things on both sides of an equation. We can also do that with an inequality. Where it gets fussy is with multiplication and division, right? So if C is positive and if A is less than or equal to B, then CA is less than or equal to CB, all right? However, if C is negative and we have A is less than or equal to B, then we get that CA is greater than or equal to CB. So if we multiply or we divide by a negative number, we flip the inequality. All right? But these are the basics, all right? And so we can do much with these. In particular, pretty much what I've just written right here will be all we need to solve linear equalities. So now we'll solve some quote-unquote linear inequalities. What's our roadmap? It's very the roadmap is this: isolate x. Okay, that's pretty much it. Just like we did for solving a linear equation, right? We solve for x. Same thing here, but now we've got to deal with inequalities. So here's an example. Example 1. Suppose you've got 3x minus 8 is greater than 15. I mean, excuse me, 7. My bad. How do we solve this? We want to solve this and we want to write the answer in interval notation, okay? So what I would do is I would add 8 to both sides, all right? So if I add 8 to both sides, that gets me to 3x greater than 15, right? Then I can do what? I can divide by 3, right? So let's divide by 3. That gives us x is greater than 15 over 3, which is 5. Now, it may be helpful, instead of writing it, I mean, you could just leave it like this and go, aha, x greater than 5. That matches this case right here, right? So we're apparently going, so that says that x is an element of, 5 to infinity. Right, so the solution set is 5 to infinity. The thing I wrote just above solution set, you don't absolutely have to write, all right? It would suffice to get x greater than 5, and then you can say, the solution set is 5 to infinity, all right? If it helps you, instead of looking at it as x greater than 5, you could also look at it as what? You could trade it for the equivalent 5 less than x, right? And maybe you see that, maybe that to you makes you think of this, right? And then it becomes obvious that you're looking at 5 to infinity. So if you're unsure of the interval, you can fall back on the number line, draw the number line. Maybe that'll help you understand which interval you need to put down for your answer, right? It's good? Okay. Example 2. Thanks. Suppose we have, let's see here, how about 13 less than 3 minus 2x less than or equal to 23. Let's see if we can solve this inequality. Now this is what you might call a compound inequality because it's got two inequalities at once, right? It may or may not be possible to solve such a thing, all right? You can write these down and make them so that they're illogical. If that happens, then the solution's the empty set. Not for this one, though. What would you do? You guys make me do all the work in here. All right, so minus 3, right? Across the board. What's that give us? I got about 10. Yeah, exactly 23 minus 3, which is 20, right? Then, okay, we want to isolate x, right? So we do what? We want to divide. Or you can think about it this way. Multiply by minus 1/2, right? Or you could say divide by minus 2. Those are the same thing, right? I like to think about dividing, you know, divide by minus 2. So we get 10 over minus 2, minus 2x over minus 2, and 20 over minus 2. And I got to be careful here, right? Because it's a negative number, I have to flip the inequalities, right? So less than becomes greater than, less than or equal to becomes greater than or equal to. And let's simplify it. 10 over minus 2 is minus 5, greater than x, greater than or equal to minus 10. Now, of course, you can write it that way, right? But I think it's just better to write it in terms of less than or equal to. It makes it easier to understand, I think. So let's flip it around. Flip it around here. So what we have is minus 10 less than or equal to x, which is less than minus 5. So what's my solution set? I heard a minus 10. I think I heard a minus 5. Do I want, which kind of brackets do I want here? Square bracket or parentheses on the left? Yeah, we want we want the square bracket because minus 10 is included, but we want the parentheses because minus 5 is not included. Right? And there you go. That's the answer. This is the solution set in interval notation. I should mention, before I forget, excuse me, you may have had a course before where they use this kind of notation rather than like we're using this, yeah? Or maybe you used, maybe you also used one of these guys, whereas we use this, at least in the book. Excuse me. If you go looking in my solutions on my website, like older things I've done for this course, you may encounter the other notation for number line. So there's another notation. Number line sets, intervals. And I actually kind of like the open dot, closed dot method. Why? If you remember previous math that you did, remember when you did graphing? You sometimes had like the endpoints filled in or opened. That's the same idea. On the flip side of things, I do understand why they like to use these parentheses or the square brackets here, because it exactly mirrors what you need to put for your interval, right? You can kind of, you know, I guess you can more or less see it here, right? Like this interval from A to B with A included, B excluded, it's just the same over here, right? The pattern's the same. But you got to be careful, right? That your solution's written in terms of less than or equal to, or less than, otherwise you could get turned around, like here. Right? This would not be minus infinity to 5, would it? It's not, no. Okay. Let me move along here. Oh, I should mention there is, I'm pretty open-minded. You might be like, well, so students usually ask me, so could I use either notation on number lines if it was like a test or a quiz, you know? Yeah, I would be fine with either, right? There's only one notation I will not allow. I tell this to all my sections. It's the French notation. See, the French, some of the French at least, they write this for this. And I can't allow it. I forbid this notation. It's too horrible. It's too horrible. And that's the question I asked the other sections. Do you guys know any French people? No. Okay. You know, so you know French, but not French people? No. Yeah. So far, I haven't found anybody who knows any French people. Except possibly their French teacher. I don't know. Actually, there's nothing more humorous than being taught a foreign language by somebody with like a strong Southern accent, right? Have you seen it? Seen it happen? Yeah.
We just had French exchange students when I was in high school.
Oh, okay. Hey, that counts. Did they ever talk to you about this? No. France. They made you French cookies, crepes. Let's see here. Of course, we all love French fries. Sorry, I'm an idiot. Let me go on here. Example 3. What if you were going to solve, say, x plus 3 divided by minus 7 greater than, oh, I don't know, 2x? How would you solve this one? So my 7's getting too far away from that. There we go, minus 7. All right. So what should we do? Multiply by negative 7. I like it. Now when we do that, we have to be careful to do what? To flip the inequality, right? So we got x plus 3 less than minus 7 times 2x. Let's clean it up a bit. That's x plus 3 less than minus 14x. So I'm going to add 14x to both sides. All right. I mean, there's a few different ways you could go here, but I'm going to add 14 And if you want, we could do it all in one step. What else should we do while we're at it? Subtract 3. Right, yeah. If we add 14x and subtract 3, that'll get us where we want to go. The 3's will cancel. We'll get 15x less than minus 3. All right. And now we can divide by 15. What happens then? Do we have to flip the inequalities this time? Nope. So we get x less than minus 3. But there's a minus 3 there, though. Well, let's be careful, right? The flipping depends on what you're multiplying or dividing by. The presence of a negative in the problem doesn't make you flip it, right? It's when we're multiplying or dividing by a negative number that we have to flip the inequality. Yeah? And there you have it. So what's the answer? Solution set. Minus infinity all the way to minus 3 over 15. Oh, we could simplify that, right? What's that? Yeah, minus 1/5. Sorry. Minus 1 over 5. There you go. So, by the way, this problem come up on a test. You leave your answer as 3/15 rather than 1/5. Am I going to take a point off? Probably not. Unless it keeps you from seeing some other simplification. All right? If it's, you know, part of a larger story, I might take something off. But if it's just that alone in the final answer, I don't much care that much if you leave it as 3/15. All right. Another example here. Example 4. Let's see here. Suppose we have 1/2 x plus 1/3 x plus 1/5 times x plus 6 is greater than 1/10 x. How would you handle a problem like this? I mean, we could add the fractions, right? I don't recommend that path. We want to get rid of the fractions, right? Fractions are our mortal enemy. Destroy them. How do you destroy them? We could look for a least common multiple of 2, 3, 5, and 10, right? 60. I guess 60 would work, right? Like 60 over 2 is 30, 60 over 3 is 20, 60 over 5 is 12, 60 over 10 is 6. I think we could be lazier than that. What will be less than 60 would also work to make all the fractions go away. I heard a 30? Yeah, let's multiply by 30. So then we get 30 over 2x plus 30 over 3x plus 30 over 5 times x plus 6 greater than 30 over 10x. Let me clean it up a bit. 30 over 2 is 15x plus 10x plus 6 times x plus 6 greater than 3x. I probably should multiply through the 6 here, right? 15 plus 10 is 25. So I've got 25x plus 6x plus 36 greater than 3x. So I really have what? I really have 31x plus 36 greater than 3x. We want to isolate x, right? So what should we do? How about subtract 3x from both sides? We could do that, right? You guys are like, I'm still writing everything you wrote. Give me a second. Fine. I will pause. You guys with me? What should we do? How about subtract 3x? Okay. And we could also subtract 36, right? If we do that, this will give us 28x greater than minus 36. Now we want to isolate x, right? So divide by 28. What happens? We get x greater than minus 36 over 28. Does that I think that simplifies. Like we can factor a 2 out, right? That's like minus 2 times 18 over 2 times, oh wait a minute, we can factor a 4 out, right? Yeah, 4 over 9, and that's 4 times 7. So as you just told me, it is in fact minus 9/7 in disguise. So we have minus 9/7 is less than x. If we want to flip it around, and I do, because then I can clearly see that we're looking at the solution set minus infinity. Wait a minute, my bad. Minus 9/7 to infinity, right? I got one more of these examples for you guys. Unless there's a question about this one. Okay. Example 5. We could have something like 10 plus x less than 13 minus 2x, all right, less than minus 3 plus x. All right. Let's try to solve this. So when I run up against something like this, the first thing I do is try to put all my x's in one place, right? So the natural thing to do for me here is to subtract x across the inequality. So I'll subtract x here and here and here. Yeah, do it everywhere to be fair. And that gives me 10 is less than 13 minus 3x is less than minus 3. All right, you gotta be on the watch out for something like this. See a problem like this, you don't need to go further. You stop right here. All right, you stop right here because look at this. See this? So there's another law of inequalities. I don't know if it's so much a law as it's just, well, I don't know. If I tried to write this down as a general rule, it would probably be confusing to you, but I think you can see it if I show it to you, right? If this is true, what does this say? This means that 10 is less than minus 3. Is 10 less than minus 3? It is not, right? Which means that the problem as stated is nonsense. There is no solution. Which is to say, the solution set is the so-called empty set, which sometimes people use this notation for as well. So it's the set containing no elements. That's the solution set in this case. It's good? So one of the other sections at this point in the lecture said, oh man, this is so much better. Now, that person's not right, because anybody who feels better about inequalities than equalities is not quite right. Like, there's something intrinsically more difficult about inequalities than equality. It's just true. You think it's way easier? Uh-oh. Sorry. But what they were really, I understood their comment, and what they were really, but wait a minute. On the flip side, if I was to take the inequalities away and trade you for equality with the same algebraic patterns, you would agree that that's way easier, right? Yeah. I mean, that's the thing we did. That's the thing we did in like 5 minutes at the end of like the first week, right? We spent all of about like 3 minutes on how to solve linear equations. It was section 1.1. Really, we should have put that at the start of the course because it's the easiest thing we've done this semester by far, right? You know what I'm talking about? This one, like 3x minus 11 equals to 2, solve for x. Done, okay? This we can all do, right? I think if you add inequalities, it makes it worse, right? I mean, agreed. I'm trying to redeem my comment towards you guys. But what he was really saying is, oh, it's just such a weight off my shoulders to not be factoring today. That's really what his comment was. See, because the thing we did last week was factoring. And if you don't have all of your ducks in a row, so to speak, factoring is very scary because there's a lot to learn there if you haven't learned it already. Well, I have bad news. Factoring is coming back. In fact, factoring will never leave us in this course. We will be factoring the whole time. It's not going to go away. So the inequalities I've solved so far have been linear inequalities. We could solve them just using the laws of inequalities that I erased, all right? Nonlinear inequalities, on the other hand, require a different strategy. So let's talk about them. Nonlinear inequalities. So let me give you the roadmap here. Here's our technique. Technique to solve. All right, so I'm going to describe it as a 4-step process. All right, step number 1 is to identify all algebraic critical numbers which come from either 0 or division by 0 in the given expression. All right, so number 1, we have to identify all. I said algebraic critical numbers, but we could call them critical numbers because we're only going to talk about algebraic critical numbers in here. All right. If you took calculus, you'd have a reason to distinguish between what you could call algebraic critical numbers and critical numbers in the sense of calculus. Those would be a little bit different. But, you know, hey, we're not doing calculus, so we can just call it a critical number. No harm, no foul. Step number 2, you write all critical numbers in order on a number line. That's step number 2. All right. And listen, this probably doesn't make a lot of sense with me just writing it down, but I'm going to bring this algorithm to life with examples right after we're done writing it, okay? But I just want to set it down here so you can see what's happening in each example past this point, okay? Step 3, you test a point between well, let's say we test a point in each case between the critical numbers. And that doesn't quite do justice, like the language. I mean, really, you need to test a point in each case. And when I say test a point, and write either plus or minus as appropriate. From the expression. So you're testing the expression that you're given to start with, okay? All right. Now I need to write a little caveat here. We'll use the sign flip trick, which says odd factor flips, even factor no flip. All right, it'll be a little bit before I really blow up that green comment, but it's very labor saving. And then step 4, write down the answer. Now, I should mention, so you guys are the last section I teach this material to. That gives you the benefit of me thinking of something I haven't told any other section yet, which is unfortunate I didn't. But what I should have told them at the start is we're solving stuff greater than 0 or stuff less than 0, all right? But the pattern is stuff, either greater than or less than 0. The point is you've got everything isolated and you just have 0 on one side and everything else on the other, okay? That is the context of all the examples that are about to follow, all right? Okay, hey, let's get into it then. I think I'm on example 6, is that right? So let's solve x squared minus 3x plus 2 greater than or equal to 0. This is a nonlinear inequality because it involves powers of x, right? And as I was forecasting, factoring, come back, yeah. So, but this one's not too bad. Just what, x minus 1 times what? You guys can factor this one, right? X minus 1 times x what? X minus 2, right? So identify critical numbers 1 and 2. Critical numbers here are 1 and 2. That's what makes the expression 0. How about either come from zeros or division by 0? Is there division by 0 possible in this expression? Like, no. Remember those questions we asked about domain? Remember? Domain was only interesting for like rational expressions. Domain for polynomials, just all real numbers, right? So like, there's no division by 0 in this one. It's just the 0 thing. So, all right, then what? Then, so we've done step 1. Now we need to do step 2. Step 2 says, draw a number line, like so. Put the numbers in order. Which comes first, 1 or 2? 1? Okay. It's not like, is this a trap? this is a trap, isn't it? You thought it was 1, but in university we learned that 2 comes before 1. No, it's not it. It's 1 comes before 2. I asked the other section if they'd ever known anybody who had their second birthday before they had their first. So far as I know, nobody. Although I guess really it just requires the purchase of the wrong candle, right? Think about it. So then what? Okay, so then we've done number 2. Now we test a point in each case. All right, so I'm going to explicitly put the points here. It turns out we don't need to always do this, but I'm going to do it this time. So I'm going to try 0 here. I'm going to try 1.5 here. And 3 is over here, so I can use that one, right? Now, I don't always write this part out. I think about this in my head. So plug 0 into the expression. What do you get? We evaluate the expression here, x squared minus 3x plus 2 at 0. We get back 2, right? Plug in x equal to 0, you get 2. So for that reason, I put pluses here because 2 is positive. Now if I plug in 1.5, I get 1.5 minus 1, which is 0.5. And I get 1.5 minus 2, which is minus 0.5. So I've got a plus times a minus. That's a net negative. Minus between 1 and 2. So I put some minuses here like so. You can put as few or as many minuses as you want. All right? Like, why is it 4 minuses? Why is it not 3 minuses? There's no good answer to that. Just decoration. 3. Plug in 3. 3 minus 1 is 2. 3 minus 2 is 1. So 2 times 1 is 2. It's positive. Again, here, pluses. All right, so we tested 3 points. And I just made a little notation on the number line to tell you what points I was testing, okay? If you look at my solutions from past years, you'll find that often I just write a number line without even putting in test points. I just think about a test point in my head. I don't even write it down. But it's a good habit to write down the test points. It's an even better habit to write off to the side somewhere your actual evaluation of the expression at the test point. That way, if you get it wrong, I can give you partial credit, you know? Okay. Now what? We're done with 3. Write down answer. Solution set is what? So we've got minus infinity to 1, and we include it. Why do we do that? Why do we include 1 and 2 here? We're solving greater than or equal to, right? Equals to 0 is a case we want. When x is equal to 1 or x is equal to 2, the expression is 0, right? So we do need to include those in the solution here. And that's it. So you notice a new character has entered the scene. This right here is union, right? If you didn't know, I'll remind you. A union B for 2 set. If we have a set A union with a set B, that is by definition x such that x is an element of A or x is an element of B. And that's mathematical or. So it's not, you know, it could be in one or both, right? Now, you could get a solution set like this from a pair of linear inequalities, right? But we'll get back to that. Let me not do that right now. Any questions about this? Obviously, I have not explained the sign flip yet, right? Let's try another, okay? Example 7. Suppose we're solving, I don't know, x minus 3 quantity squared times x plus 2 to the 3rd power divided by x to the power 5 times x plus 10. to the squared. You know, I have blocked so many of them, but it doesn't matter. I do not need movers. I've already moved. Thank you. Let's see here. All right. So here, and what do you guys want? Greater than or less than equal to 0? What do you want? Less than or equal to 0. Very good. Now, I did the hard part, right? It's already factored. Yeah? So that means we can read off the critical numbers. Critical numbers are what? We've got a 3. But remember, it's what makes this 0. So it's not 2, but it was not minus 3, right? It was 3. It's not 2, it's minus 2. Down here, 0. 0 itself is a critical number, right? And minus 10. All right, so if we're going to draw a number line, we want to put those in order, yeah? So you guys tell me which one is most left on the number line? Negative 10. Very good. Then what comes next? Negative 2. Very good. Then 0, right? And then finally 3. Okay, so what you guys, let's test a point here. Let's try out 1. That would be here, right? So if we try plugging in 1, what happens to this expression? So I'm gonna write it over here because it's right over here. If we plug in x equals to 1, what do we get? We get 1 minus 3 quantity squared, 1 plus 2 quantity cubed, divided by 1 to the power 5, 1 plus 10 squared, right? If we plug in x equal to 1, this is what we get. Which is what? Minus 2 squared. So think about it. This is positive, positive, and then downstairs, positive and positive, right? So we got pluses all around. So altogether, it is a positive value. So in short, between 0 and 3, we have positive values. The idea here, guys, is that the expression can only change from plus to minus when your graph crosses either the x-axis or a vertical asymptote, right? The vertical asymptotes are coming from division by 0. The zeros are coming from, well, the numerator being 0, actually. But anyway, we're not talking about graphing yet. I'm just saying, if you want to understand where this technique is coming from, it's really coming from our understanding of graphs. All right. And there's also something about a hole in the graph, but we'll get back to that. All right. So that's positive. Now, what would happen if we plug in minus 1 instead? Minus 1 would be over here, right? So if you plug in minus 1, what happens? We get minus 1, minus 3 quantity squared, right? Minus 1 plus 2 quantity cubed, minus 1 to the power 5, minus 1 plus 10, and so what happened there? So we've still got positive for this, because it's a square. That's 16. This gives me a 1. So positive, positive. Oh, but look at this. Minus 1 to the 5th, it's negative. And that's positive again. But look at this. You got an extra minus, and so all it takes is 1 minus If you have an odd number of minuses, you get negative, right? So from plugging in -1, I get minus here. All right. So I'm now going to use the sign flip theorem to fill out the rest of it, all right? Watch this. See this 3? With x minus 3? It's a square. What that means by the sign flip theorem is that as you go across the number 3, you're going to stay plus. You don't flip signs. It stays plus. Now, if you don't believe me, you could try plugging in 4 and see that you get a positive. Okay. You can actually just kind of think through that here. If you plug in 4 instead of, if you plugged in 4 here, that's positive, that's positive, that's positive, that's positive. So you got plus, 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 plus. 2 pluses upstairs, 2 pluses downstairs. You got a net positive, right? But I don't have to do that if I understand the sign flip theorem, which says that if you have even powers, you don't flip sign. If you have odd powers, you flip sign. How about this? 0. What was 0? 0 was a 5th power. That's odd. So I can view that as the reason that I changed from plus to minus here, going across 0. Either way you look at it, left to right or right to left. We flipped signs there. Because x to the 5th is an odd power. Right? In this previous example, this is to the 1 power. That's to the 1 power. Right? These are odd powers. What happened here? Every critical number is a place where you flipped from plus to minus. Yeah? Okay. Now, how about this? You guys tell me. -2. Are we going to flip signs there or not? Well, but be careful. It's not the number, which is even or odd, that matters. It's the power that's even or odd. So we look at the 3, right? And we are, because 3 is odd. So we do flip signs from minus to plus here. How about -10? Flip or not flip? Look at the factor it came from. It came from x plus 10 squared. So that's doesn't flip because it's x plus 10 to the power 2. Yeah.
So we didn't flip the ones past the other line. That just stayed the same.
Yeah, because this x minus 3 is to the power 2.
Okay.
Right. Okay, so we're solving less than or equal to 0. What's the answer? Now we've finished 3 using the sign flip trick, all right? What's the solution set here? Looks like we can go -2 to 0. That's where we're negative, right? Now this one is a little bit trickier. We need to really think through, do we include or exclude -2 or 0? How about -2? Include or exclude? What happens when you plug in -2 into the expression? Where does it go? It goes upstairs, right? So plugging in -2 gives us a fraction which has 0 in the numerator and non-zero in the denominator. That's fine. That's just 0. Is 0 something we're looking for? Yes, it is. So we include -2. How about 0, though, itself? What happens with 0? It's in the denominator, right? If we plug in 0, that makes the denominator 0. We have division by 0. Anytime you have division by 0, undefined. Yeah.
How did you get like -2? Like how did you base the answer from?
Because the number line, I was looking for where it's negative. So that was just here.
Okay.
And the endpoints